So one of my goals today is to kind of show you a variety of integrals. I don't have a great sense from Gorski yet of how much trig he's going to do, but I do want to show you just a few of the common things that might lead us to trig. So if I look at this and I walk up to this integral and I'm going to ask myself, is it algebra, trig, or a mixture problem? And I'm calling a mixture anything that has natural log of x or e to the x is automatically a mixture problem. And anything that has a variety, like has some trig and some x to the powers, that's sort of a mixture problem. Here, that very first question that I'm going to ask myself, if I can't make it look like x is raised to powers, is the derivative of one part secretly also hiding in the problem? And it's not always easy to see with this particular one, but e to the 2x, because of our exponent rules, is actually the same as e to the x squared. And typically when we're doing integration problems, this is just a good one to kind of have in your back pocket. So we're not even doing a u substitution yet. All I'm going to do is rewrite this problem to say e to the x over 1 plus e to the x squared. And having written it like this, now I can say, oh, hey, is the derivative of one part hiding somewhere else in the problem? Yes, it is. If I come off to the side and build my vocabulary list, and u is equal to e to the x, then du would be e to the x dx, because I'm taking the derivative to go from u to du. In terms of translating our problem, I have that e to the x dx that will turn into my du. And the bulk of the problem here, now this e to the x, that's my u, which means this looks like 1 over 1 plus u squared du. And now that I've translated it, I'm going to find the antiderivative. This guy is one that you should memorize if you haven't already. In 17a, typically, we don't deal with all 6 inverse trig functions, but we do tend to deal with inverse tangent. And the reason is that this integral pops up a lot for us in 17b. So it's important to know that 1 over 1 plus u squared is the derivative for arctan or inverse tangent of u. So I'm going to get tan inverse of u plus a constant, and then our final step in that u substitution is to go ahead and plug back in what our u was so that we're answering the question in x's. So I'm going to have tan inverse of e to the x plus a constant. And if you haven't found it already, in Canvas, when I added my generic ones, when I added like my version of the generic antiderivatives, I added 2 in there for arctan, just because this does tend to be one that shows up a lot in 17b. So now we're talking about a definite integral because I have limits of integration. If I walk up to this integral and I ask myself, is it algebra, trig, or a mixture of stuff? It's a mixture because I've got this algebra piece and this natural log piece. I first want to ask myself that question, does the derivative of one part equal the other part? Well, the derivative of x cubed is definitely not going to give me a natural log. And the derivative of natural log of x would be 1 over x. So that's not going to take care of the x cubed. This is not a u substitution. Instead, I'm going to think to myself, oh, integration by parts. So in terms of integration by parts, I'm going to follow that rule of late. So in this case, I've got logs and I've got algebra. And I'm going to say who comes first in the word late? It's the logs. So when I go ahead and do the integration by parts work on this, I'm going to let ln of x be my u. Well, if u is natural log of x, then when I take the derivative, I'm going to get 1 over x dx. And if natural log of x is my u, then everything else had to be dv in terms of our integration by parts formula. So dv is going to be x cubed dx. And since our integration by parts formula takes a u dv and turns that into uv minus the integral of v du, in order to use this formula, I also need to know what v is. Well, if v is x cubed, if dv is x cubed, then when I find that antiderivative, the antiderivative of x cubed is going to be 1/4 of x to the 4th. Now I'm going to plug these parts into our formula to try this integral for a different one. Well, my u is natural log of x. V is 1/4 x to the 4th. I'm going to be subtracting off v, so that 1/4 x to the 4th times du. And du was 1 over x dx. One of my tips for doing integration by parts is after you've written this, you always want to simplify this as much as possible before you try to find the antiderivative. So in this case, simplifying that is going to look like there's nothing we can do to that part out front. But here I can take that 1/4 and bring it in front of the integral. And x to the 4th times 1 over x is going to make this x cubed. Now I'm ready to find the antiderivative here. If I add 1 to that exponent, I'll have x to the 4th. And then dividing by that new exponent means that I've got that 4 in the denominator and another 4 in the denominator. So that'll be a 16. Now I'm not putting a plus c on this, because if we come all the way back up to the beginning, this was a definite integral, so I have bounds to plug in, which means I'm now going to draw my vertical line and be plugging in the 1 and the e. Just as a point to be careful about, when we're doing integration by parts, or rather, whenever I have a definite integral and I've got values here, then when we're done, we're expecting to get a number. I shouldn't have x's left in the problem, which means that when we do integration by parts, that first piece, even though we didn't really have to integrate that to move on with our formula, this is still part of the antiderivative, which means the e and the 1 have to get plugged into it. I did not leave myself enough space here, but I'm gonna try. So I'm going to plug in e and subtract off plugging in 1. We'll see how it goes. But I'm kind of going to talk through this. So if I plug in e, natural log of e is 1. So then I'll have 1/4 e to the 4th minus 1/16 e to the 4th. Now I'm going to plug in the 1. Well, the natural log of 1 is 0. So it doesn't matter that this is 0 times something. It's still going to be 0. When I plug the 1 in here, I'll end up with 1/16. So we've got 0 minus 1/16. This is just algebra, meaning all I have in this problem are numbers and x's raised to powers. And if there's just algebra in the problem, then oftentimes there's an algebra solution to get through the integral. And here, my algebra solution is to look at the bottom and notice, oh, hey, it factors. So if we rewrite the denominator as 1 over x plus 1 whole thing squared, now suddenly I've got something to work with. Two options for how we get through this. Option 1 is we actually write out a u substitution. Option 2 is we kind of recognize what the u substitution is going to be and do it in our head. So I'm going to write out the u substitution the first time, though I'll be honest, that's not the way I would do the problem. Here, if I were going to write out the u substitution, I'd be asking myself, hey, does the derivative of one part equal another part? And the piece whose derivative is in there, if I make u x plus 1, then du is 1 dx. And I have the 1 dx, which means we can rewrite this in terms of a u substitution as 1 over u squared du. Or u to the negative 2 du. Now if I find the antiderivative, I do have like a something raised to a power, which means I can add 1 to that exponent. When I add 1 to negative 2, I get negative 1. So I'd have u to the negative 1 divided by negative 1 plus a constant. And then wrapping it all back together, because the question was asked in terms of x's, I need to return my final answer in terms of u's. So I'd have x plus 1 to the negative 1. And dividing by negative 1 is the same as just making it negative. And the more common way to write this would be to eliminate that negative exponent by writing this as negative 1 over x plus 1 plus a constant. I said this isn't actually how I would do the problem. It sort of is, but I would skip the step of formally writing out the u substitution. And the reason that I say that is if my u substitution is going to be x plus a number, chances are good you can probably do that u substitution in your head without writing it out after a little bit of practice. So this line, if I had just thought about writing that as x plus 1 to the negative 2 dx, I can recognize that it's going to be a u substitution. But if u is x plus 1, then the derivative is dx. So I can kind of skip to the step of saying, I'm going to add 1 to that exponent and divide by the new exponent. And even if this had been x plus 4, then the derivative of x plus 4 is still just 1 dx, which means this would become x plus 4 to the negative 1 over negative 1. And I needed to find the antiderivative of this. We can absolutely do a u substitution here. And I'm going to write it out with a u substitution, and then we're kind of going to generalize it. It's just x's raised to powers. And if I think about, does the derivative of one part equal the other part? The answer this time is kind of no, but we're only off by a number. And if we're only off by a number, chances are good a u substitution is going to work. So here, I'm going to set my denominator to be u. And if u is equal to 3x plus 5, then du would be 3 dx. I don't have a 3 dx in the problem. I have a 2 dx on the top. So there are a couple of options. We can pop the 2 out front, or we can turn the 2 into a 3. It doesn't really matter. I happen to think it's a little bit cleaner to pop the 2 out front. And if I pop the 2 out front, then that means I'm not going to be replacing 3dx. I'm only going to be replacing the dx in the problem. So I'm going to go ahead and divide both sides by 3, which means dx is equal to 1/3 of du. And when I do this substitution, I move that 2 out in front. In the numerator, I end up with a 1/3. And then I've got that du. And if I want, I can move that 1/3 out in front also and write that as 2/3 times the integral of 1/u du. And then look at that and say, oh, whose derivative is that? That's the derivative of natural log. So I would get 2/3 natural log absolute value of u plus a constant. Putting that back in terms of x's, because that's how the question was asked, I'd end up with 2/3 natural log absolute value 3x plus 5 plus a constant. If I generalize this a little bit more, anytime I have a linear term in the denominator, I see a question, I'll get to it momentarily. Anytime I have a linear term in the denominator, meaning something that looks like ax plus b, and I'm just going to write it generally like this. If there were a number on top, we could pop it out in front of the integral. But anytime I have something that looks like this, I know that that u substitution, oh, thank you for answering the question. I know that that u substitution will end up to be u is equal to ax plus b, which means my du is a dx. And when I go to fill that in, I'm going to divide both sides by a because it was some constant, so that I end up with 1/a du is equal to dx. Turning this whole thing into 1/a times the integral of 1/u du. 1/u, as was pointed out in the chat, is the derivative of natural log. Since we're finding the antiderivative here, I'm going to get 1/a natural log of u, and I'm going to go ahead and just plug that u in, ax plus b plus a constant. I'm going to walk up to this integral, x divided by the square root of x plus 4. And I'm going to ask myself, is it algebra, trig, or a mixture of stuff? And the answer is it's just algebra because I've only got x's. So I'm hoping there's some kind of algebra that we can do. Unfortunately, I can't do a whole lot with that square root because I've got addition inside of it. So I'm kind of going to switch gears and say, well, if there's not much I can do with that algebra-wise, does the derivative of one part equal another part of the problem? And the answer is, yeah, kind of. So if I take the part of this that's the ugliest, meaning the square root part, if I were to let u be equal to x plus 4, then du is equal to dx, or 1 dx. Thinking about this as my vocabulary list, I now know what to do with the x plus 4, and I know what to do with the dx, but my vocabulary list hasn't yet told me what to do with the x that remains in the numerator. But if u is equal to x plus 4, then that must mean that x is equal to u minus 4. And I can translate this entire problem into something with u's. So that x on top can become u minus 4. The dx can become du. And that denominator can become the square root of u. And you might be looking at that and thinking that doesn't look a whole lot better. The good news is it is better. If I have a single thing in my denominator, then I can break this apart as separate fractions. So if I rewrite this now as separate fractions, u over the square root of u minus 4 over the square root of u, each of those I can write as a u raised to a power. So u divided by the square root of u is going to leave me with u to the 1/2 power. And 4 divided by the square root of u is going to leave us with 4u to the negative 1/2 power. Just thinking about simplifying the exponents. Now I can find the antiderivative, add 1 to the exponent, divide by the new exponent, to end up with u to the 3/2 divided by 3/2 minus 4u to the 1/2 divided by 1/2 plus the constant. And always remembering that when we're done, we want to make sure to rewrite our final answer back in terms of x's, because that's how the question was asked. I'm going to go ahead and take that division by 3/2 and write that as multiplication by 2/3. U was x plus 4. Here, division by 1/2, the same thing as multiplying by 2. So I'll have minus 8, and then x plus 4 to the 1/2 power plus a constant. Sometimes this is called back substitution, because we make a substitution, but then there's still an x left over that we have to go back and solve our u substitution for x to plug in. So my next integral, I've got x squared times cosine of x. I walk up to this integral and I'm going to say to myself, is it algebra, trig, or a mixture of stuff? Well, this is a mixture. I've got this algebra piece that's x's raised to powers and this trig piece in that cosine x. It's a mixture problem, so I'm going to ask myself, does the derivative of one part show up somewhere else? Well, the derivative of x squared is 2x, and the derivative of cosine is negative sine. So neither of their derivatives are in the problem. It must be integration by parts. Since I've got a mixture of algebra and trig, again, I'm thinking about late. Algebra comes before trig in the word late, or A comes before T, which means that A piece will be my U. I'm going to come off to the side. U is going to be x squared. I'll take the derivative to get the du part, 2x dx. And then everything else has to be dv. And the everything else is cosine x dx. Well, now I ask myself, whose derivative is equal to cosine? Positive sine. Popping that into our ultraviolet voodoo formula, as in uv minus the integral of v du. I'm looking at x squared times sine x minus the integral, the voodoo part, v du. So minus the integral of sine of x times 2x dx. I mentioned before that whenever we're getting ready to move forward, we should always simplify this as much as we can before we try to find the antiderivative. Here, I think the only thing we might choose to do to simplify is to move the 2 out in front of the integral. There isn't really anything else we can do to this. So I'll go ahead and put that 2 out in front of the integral. So now I look at this as an antiderivative problem and say, hey, is it algebra, trig, or a mixture of stuff? Well, it's still a mixture because I've still got algebra and trig. So then we ask ourselves, does the derivative of one part equal the other part? Well, the derivative of sine is cosine, so that's not going to help. And the derivative of x is dx, but that wouldn't tell us what to do with the sine of x. So we're stuck. We're going to have to do integration by parts a second time. Looking at this integral, I'm going to come off to the side and build our pieces for integration by parts. Again, algebra comes first in the word late. I'm going to let u be equal to x, which means du is dx, and everything else has to be dv. So dv is going to be sine of x dx. I'm looking at that sine of x and I'm saying whose derivative is equal to positive sine of x? That function we need is negative cosine. Putting that all together, and I will say whenever we're having to do integration by parts multiple times, it's super important to be organized on your paper and like use the entire line or more than one line. Use a whole half a sheet of paper. Use a whole sheet of paper if you need, but staying organized really can make a difference in these problems. So I've got x squared sine of x minus 2 times, and now I'm going to give myself some big brackets. That 2 applies to this entire integral. And this entire integral is what we're replacing with ultraviolet voodoo. This entire integral is what we're replacing with uv minus the integral of v du. My u is x. V is negative cosine of x minus the integral of v negative cosine of x du dx. And there we go. I mentioned before, and now is the time to utilize it. Before we move on to find an antiderivative, it's super useful to simplify this out as much as we possibly can, especially trying to keep track of all those minus signs. So I've got x squared sine of x. And now this negative 2, I'm going to go ahead and distribute it into my first piece and my second piece. So when I distribute the negative 2 into this, the negative 2 times that negative cosine of x is going to leave me with positive 2x cosine x. When I distribute that negative 2 back here to the second part, first of all, I've got minus a minus here, which would make this a plus, that integral. And then I'm distributing the negative 2 in. So overall, that's going to leave me with negative 2 times the integral of cosine x dx. There aren't any additional simplifications that I can make, so I'm ready to find that final antiderivative. So copying all these parts down because we're already done with those. They were part of our formula. The function whose derivative is cosine is positive sine. So I'm going to end up with negative 2 times positive sine of x plus c. Okay, here's my function, or here's my integral. We're going to integrate e to the x times sine of x. I walk up to my integral. I ask myself, is it algebra, trig, or a mixture of stuff? It's a mixture of stuff. Derivative of one part is not equal to the other part, so I'm already looking for integration by parts here. So I have a mixture of exponentials and trig. I'm going to follow my late rule. And since trig comes, or t comes first in the word late, I'm going to let the trig part be equal to my u. If u is equal to sine of x, then that derivative is going to be cosine of x. And everything else in the problem has to be dv. So my dv is going to be e to the x dx. I'm going to take the antiderivative here and get that v is e to the x. So we're swapping out this integral for ultraviolet voodoo, u times v minus the integral of v du. So I'll have sine of x times e to the x minus the integral of e to the x cosine of x dx. Quick check, anything we can simplify? I'm going to go with no. So now I'm looking at this new integral I have and thinking, okay, is it algebra trig or a mixture of stuff? Well, it's still a mixture problem. In fact, it's still a mixture of an exponential function and a trig function. And I'm going to follow that rule of late one more time and say I'm going to let my trig be my u. And if u is equal to cosine, I don't have a ton of space here, I need it all. If u is equal to cosine of x, then du must be negative sine of x dx. And if dv is e to the x dx, then v must be e to the x. Just like we did on that previous problem, I'm going to rewrite this. So I'm looking at, and I'm just going to swap the order on these so that I don't need the parentheses anymore, and write that as e to the x sine of x minus, and then just like on the other problem, I'm replacing everything inside of that integral. We're going to replace it with u times v, so e to the x cosine x minus the integral of v du. So e to the x times negative sine of x dx. And before I go to integrate anything, I want to simplify this as much as possible. So I've got e to the x sine of x, and I'm going to think about distributing that minus sign in. So when I distribute it to the first piece, I've got minus e to the x cosine x. When I distribute it to the second piece, I've got a minus, which makes that plus, and then that extra minus turns it back into a minus, the integral of e to the x sine of x dx. Now, if you followed me this far, you might have noticed that's exactly where we started. Because over here, back at the beginning, we started with the integral of e to the x sine x dx. It's not a mistake. It's math magic. And the math magic here is that I can pick up this entire piece, and as long as I do the same thing to both sides of that equal sign, we won't have changed the problem. So I'm going to pick this entire piece up, and I'm going to add it to both sides of the equation. That means that on the left-hand side, I won't just have one of this integral, I'll have two of them. So when I add that to both sides, I'm going to end up with 2 times the integral of e to the x sine of x dx is equal to e to the x sine x minus e to the x cosine of x. And that's almost what we were looking for at the beginning of the problem. The only extra thing that I have to do is now divide both sides by 2 or multiply both sides by 1/2 to get the integral that we wanted all by itself. And I almost left myself enough room to do that. But I'm going to divide both sides by 2. And then say, hey, we're done, plus c.